Hello and welcome to CppCon. My name is Basit Ayantunde. I'm a student at the University of Ilorin in Nigeria. I have taken a number of internships and I recently completed my internship at Goodman Sachs, where I wrote software for managing some of the high-performance data engineering systems. I've been in the embedded space for about 3 years now, and I started out as an hobbyist embedded developer. I have in some previous projects written embedded drivers for mini robots and for really small robotic systems. I've also been contributing to open source projects for microcontrollers like SIM6NN and TensorFlow Lite Micro. I've recently been getting more interested in exploring the operating systems field of lately. So, yeah. First, the goals of this talk. Let's go through some of the goals for this talk. First of all, we want to perform a brief introduction into STX, its optional value and functional error handling and reporting facilities. Goal number 2 is to encourage you to rethink and pay more attention to error handling and reporting in your code base. Goal number 3 is to briefly illustrate the logic abstraction capabilities of this type model that I'll be introducing to you later today. So first, a disclaimer. STX panic option and results aren't totally my ideas, but rather a unified and refined form of the error handling techniques that we commonly use today in C++ projects and outside. So a brief overview of the embedded system space, on some design considerations that are usually used for writing software. We try to maximize performance and utilization of the hardware. And we try to make the firmware as secure and memory safe as possible. Another one is we try to have strong failure and safety guarantees unlike normal systems. And we have very, very small memory and storage constraints. You can have embedded devices with like 34 kilobytes of RAM. And basically, it's very, very small amounts of RAM, 128 kilobytes, etc. So you have to pay close attention to your code and what features and facilities you pull in. Also, we also pay more attention to toolchain and feature completeness, because every toolchain, some toolchains, for example, don't fully implement exceptions and some other libraries. So you have to test and be sure of what you're doing. We also do have some hard real-time and software real-time constraints. In hard real-time software, we try to make sure we know exactly the execution time of the functions and be able to have strong guarantees about the execution time. If in hard real time, if the execution time exceeds a time limit, that is essentially a bug. Or like software real time, it can exceed a time limit, but not so much. And even if it exceeds the time limit, it's not a bug. So another need that we usually have in the embedded system space is to address the ever-evolving needs of the consumers and users of the software. Yeah. And also we often try to write portable code, but that's not always possible because we still need to maximize efficiency. We usually have very diverse hardware platforms. So yeah. So today we'll be introducing you to STX. First, let me try to describe what STX is. STX is a collection of libraries and utilities designed to make working with C++ easier and less error-prone. This includes, but is not limited to, well-proven and widely adopted paradigms, data structures, and designs from other prominent projects and programming language across the software engineering community. At the core, all STX libraries and facilities are no STD, no RTTI, which is one-time type information, heap memory allocation, no exceptions. So STX has a number of libraries within it, which is panic library, the optional value and error handling library, which contains the option and results type monad. We also have the backtrace library for getting function backtraces, and the platform configuration macros identification library, which is basically for identify platform macros, like detecting whether it's compiler for x86 and stuff like that, which can be error prone. Yeah. So for this talk, we'll only be illustrating the panic library and the optional and error handling library. So motivation, the reason why I started STX is because I've been working on embedded systems projects in C++, and all the projects I've worked on or contributed on are different error handling techniques. Even a single project could have different error handling techniques. In this project, we had different dynamic requirements for handling errors, especially while you don't immediately have a monitor for viewing logs to stored error, finding out your debugger or inspecting cauldrons. So I needed a library that could sufficiently solve this problem. That's why I started STX. Motivation number two is to the divergent error and optional value in C++. Some code bases with various optional and error handling type implementations, you often see them doing same things within the same code base. So I think that's basically code bloat. A recent survey showed that 50% of C++ projects ban exceptions in total or whole and use a vast variety of different error handling techniques. So basically, I think there's a need for easier, more deterministic and efficient error handling techniques, as a quote from Hab Sutter in the Zero Very Deterministic Exceptions paper 2019. He said, we cannot accept that standard C++ is not applicable for real-time systems. That would be an admission of defeat in C++ core mission as an efficient systems programming language. Therefore, we know we cannot live with today's exceptions model unchanged. Yeah. So let's take a look into fail-fast abandonment as we do it today. But first of all, another quote from Sutter: a programming bug or abstract machine corruption is never an error. Both are not programmatically recoverable. So report bugs to the human programmer using contract violations that default to fail fast, and report abstract machine corruption using fail fast. So now let's go into fatal failures. What's exactly a fatal failure? A fatal failure is a failure in which there is no known way of recovering, and in which it would be otherwise illogical and or dangerous for the program to proceed in the face of such failure. Hence, we abandon the program. Commonly today, we use stood abort for fail-fast abandonment. But the question now is that, is stood abort ever okay? Just a plain stood abort without context, is it okay? Abort doesn't really provide context nor report about the cause of the error. It optionally provides a call dump or snapshot of the system memory at the time of invocation. So let's take a look at this code. We'll define a function named ensure data okay and use it to check whether data is corrupted or not. And if it is corrupted, we'll simply abandon the program. So here's basically how we do this. We do know that the CRC title is a weak hash algorithm commonly used in embedded systems for detecting data corruption. Now, let's try to run this code and see what we get. Get aborted call dumped. I, as most users, would ask the programmer, what went wrong? I need additional information and context about the error. Even if I want to report it to you, I don't have any information to report to you. And for embedded systems, call dumps aren't always available. So that's another issue. Now, let's try to provide more context by writing the fatal error report to stored error. So instead of the previous one where we just plainly abort, at least we'll give the user a little information about the error. That's fair enough, but we were able to provide some context, and the user can now have an idea of what the fatal failure was, and that would help guide our investigation. But all we see is the error message. We don't get the source context, where the error occurred in the source code. For example, which part of code did it occur? An extremely common approach to this, which I've seen in code bases, especially ones I've worked with, is with macros. And here is how it is commonly used today. It gives the file information, the expression that caused the error, the line, the error message, and many others, which could be very useful, especially if the user is giving you a report about the error. So, if you run the code, here's what it will say. I personally really like this approach because it's even adopted in most projects that I've worked with. So but let's see if we can do more. More robust projects like Upsell and LLVM provide a customizable error hook, which is just a function you can change at runtime. This function decides how the fatal error is handled. I think it's really neat because it allows you as a user of the library to make decisions on how you want the fatal error to be handled for your project. As you can see, this function named error hook is getting a fatal error level value. So it will handle the error as a fatal error. Basically, it will find a function that is already attached as a hook at runtime and basically invoke that function. Another example in the wild, as we use fail fast abandonment today, is the zero-con kernel. It also has a fail fast function called panic, which just logs to stored error and then aborts the program. The Linux kernel also has a more complex fail fast function named panic, which turns off some peripherals. It logs the error and then performs other required cleanups as necessary. Again, I would like to emphasize that these are the needs for this project. It might not be the same for other projects. We need to manage these expectations without touching all parts of the code base. Because just for example, look at this requirement. User 1 might want to log the error report to disk. User 2 might want a detailed backtrace of the error at the point in time. User 3 might want to log the fatal error report to the console. I, as an embedded user, might want to log the error to UART or SPI or I2C or any wired protocol that I'm using. I might also want to capture the device memory at the point in time in which the error occurred and send it to the company's HQ. A user might also want to halt the executing thread so that the user can investigate the error. So there are various needs that arises as you get more users, more diverse users. So there are a number of consequences to managing these abandonment expectations. First of all, there are a number of challenges or consequences to manually hard coding these abandonment expectations. Hard coding them leads to disparities. Having many parts of the code base using divergent, error handling methods of handling these abandonment expectations. Fatal failures are often treated, especially in C code bases, as non-fatal failures to avoid addressing this problem. They just leave it to the main thread and assume the user knows that it's a fatal failure. So libraries with hard-coded fatal failure handlers often require extra effort to be usable in projects, to be integrated into other projects. And I think the important lesson we've learned here is that different projects have different needs and preferences for fail-fast abandonment. This is especially visible in the embedded and operating system space, where the needs become more evolved beyond just logging to state error. Yeah, and STX solution to this problem is the panic mechanism. A panic function is basically a configurable fail-fast abandonment mechanism for handling and reporting fatal failures, providing additional context or information about the state of the system at the time of failure, and then perform necessary cleanup routines. The panic can be seen as a fancy state abort. The panic behavior is customizable both at runtime via panic hooks and at compile time via the global panic handler. Here's the panic function and its function signature. The first overload provides a string view containing information about the cause of the abandonment. We won't be going into detail about the second argument for now. Integrating the panic into our previous example is just as simple as this. And let's see what information we'll get. Here's the information we get. We get more source level information than the previous ones. So here let's look through the information we get. We get the thread identifier, we get the function name where the panic occurred, the file name, the line number, and column number. We also get the error message that will pass through it. Yeah. So do you know that C++ doesn't have a cross-platform thread naming capability, so we just use the thread hash in the meantime, which isn't for most people of much use. Yeah. So let's say, assuming you have the STX backtrace feature enabled, if via the STX, via the CMake build file, you can enable backtraces and you'll be able to see which part of the code was being executed and the functions that were presently on the call stack at the time of the error. I find this very useful. Instead of having to step into a debugger with the call dump, and really hope you can reproduce the error data in time. Yeah. So you can also customize the panic handler, which is the primary customization point for the panic function. It is the part of the program where you perform necessary cleanups and do consistency measures. So there are a few caveats to it. First, it must only be defined once throughout an executable, which is the one definition rule. It is also not intended for definition by library developers. It is mostly meant for the high-level application developers or just application developers in general. The panic handler should be thread safe. It should be signal safe and reentrant. And you should be very, very conscious of shared state, as many parts of the program can call panic at any point in time. And it could be it could be called from a context switching or multi-threaded context. So you have to be very conscious of shared state. Yeah. So here's how you suppose your desired fail fast abandonment behavior is logged to a file. You'd write the panic handler as does. So just open the file, check if the file was successfully opened, then write the log to it. That's simple. Rather than write it from scratch, we have some helper functions that you can use to guide your implementations. We have the panic halt, which halts the present thread of execution until it is forced to resume. Probably you attach a JTAG debugger to it and set the controlling variable to true, which then resumes the program. You can also use the panic abort panic behavior, which immediately calls state abort and doesn't log anything. We can also use the panic default behavior, which logs the error report which is the default panic behavior that logs the error report to the terminal and optionally gives you a backtrace of the call stack. Yeah. If you need a more dynamic panic behavior that you can customize at runtime, you can use panic hooks, which works similarly to panic handler. This is essentially useful for dynamically loaded libraries where you don't want the DLL to decide how to abort the program. It is the primary customization it is the runtime panic customization point. It intercepts calls to the global panic handler. It is very identical to Upsell's raw login hook and LLVM's fatal error handler, and also similar to TensorFlow Lite's micro error reporter. Here is a sample code of how you use the attached panic hook. By default, the panic handler is set to panic default. So, but you are now intercepting it at runtime. So you are basically changing the panic behavior at runtime, unlike the previous example where we just defined the function. So you can just change it to any function at runtime. So in this example, we use panic halt, and it will just halt the current thread of the execution until you probably step into a debugger and inspect the program state and possibly force the thread to continue running, which immediately runs to abort. It basically also works like state terminate. So that would be all for panic. So I would like us to take a few seconds to look at this code and try to infer what this struct is meant for. Now, let me give you more context. Now take a look at it again. I'm sure by now you must be thinking this is a no terminated string pointer, but that's just what the naming tells you. We naturally rely on naming to give us some context about the code, but naming expresses our intent, not the truth about the code. Also, naming is hard, but we only try our best. Disregarding the naming, I want you to disregard the naming. The operation guarantees on this struct could be encapsulated by any of the following alternatives. Any of the following member value type alternatives. So they actually give more information about the truth and the intent of the code rather than what we say it does. This is actually what we intend to use it. This is actually what it does. So, and I would like to quote Robert C. Martin, which he said, truth can only be found in one place, the code. So I would advise you prefer strong value types that define at a high level the operations you can perform on it and possibly have well-defined lifetimes. So specifically, the truth is in what your code does, not what you intend for it to do. Let's move on to optional value handling. We have a few common techniques for optional value handling in C++ today. The most common one is the raw pointers approach, the stored optional, stored variants, and various in-house optional value implementations like Apple's optional, Fuchsia operating systems optional, which is Frito optional, and Mozilla's maybe Monad, and the LLVM's optional value implementation. So still optional has a few possibly minor issues. So here's a code comparing both techniques, pointers and stored optional. So most we claim the pointer technique is more readable and concise, but that's not, for me, that's about true. Optional value handling code is really not that easier to write with the stored optional. Here's an example of how you'd write the same code using the exception control flow instead of the Boolean control flow we used earlier. Another issue with optional that I find very problematic in my code is that it's even copies, you can't really be too sure of when copies occur within stored optional, as in the example here. If you check the assembly output for the first example, you'd notice that the containing vector is copied and the memory allocation is performed even with optimization turned on. It can be quite problematic, especially with no warnings about this. For the second example, you'd notice that we used an explicit stored move just to make sure that it is not copied. The object copies aren't really visible. You can view the Godboard link below to see what I'm trying to say here. Yeah, another major issue, I think, which is the major difference I see between these optional implementations, is the handler for fatal failures from assessing an invalid state, i.e. when you try to get a value from an optional that doesn't have a value, the handler is not really customizable. In the stored optional case, it throws a stored board optional access exception by default. Yeah. STX solution to this is the option type. Option is a safe type monad for representing the possible absence of a value. STX option is a type monad in a sense that it abstracts the optional value handling logic and thus make handling the null and value states easier and provide clearer optimization path for the compiler. Another advantage to option is the clarity of intent, the readability and composability of this type monad. Yeah, the option struct is basically implemented as a union with a tag discriminant Boolean that tells us whether it is a non or a value variant. The option struct has a few constructors. The sum type is used for tag dispatch to the value variant state, and the non type is similarly used for tag dispatch to the non-variant state. It also has some move constructors and copy constructors as usual. So let's see some examples of option. To obtain the value from the option, we use the unwrap method call, and to provide an alternate value in case the option is in a non-variant state, we use the unwrap or method as shown below in the second line. For handling both the scenario where a value might be present or not present, we use the match method as shown below. Yeah, so as we can see here, the option is a type monad. By that I mean a type with methods to abstract actions. It does basically makes error handling code easier to write and directly expresses intent without having the error handling or option handling noise. Let's look at one of the monadic methods, which is the map oils method. It applies a function to the contained value if any, or computes a default if not, which is the second function argument. So here is how you write the code with option, and the second one is the one with pointers, and the third one is the one with stored optional. As we can see here, STX options, it directly expresses the intent. Yeah, I would also like to illustrate one of the optional value handling abstraction capabilities of monads. In the code here we are chaining multiple fallible operations that have option as a return type. The add xxx is basically add tie, add hat, add shoe, add glasses to a person. So we have a person object. We want to style the person by adding various items to the person, but it won't return the person object if any of the operations fail, which basically makes it fallible. Now, here's how we do just that with the and then method of the option type monad. And here is the equivalent code of how you do that with stud optional. As you can see, stud optional's code is quite noisy. You note how we are more clearly expressing intent by using the option monad for control flow, and at the same time reducing the noise in the code in progress. Another reason why you might consider option is that unlike stored optional, it doesn't throw exceptions in case of a request for a value and there is no value present, but it calls the customizable global fatal failure handler, which is the panic. Option has tons of other monadic methods that can abstract away the optional value adding logic. You can explore for yourself in the URLs, in the project URL below. Hello, and let's move on to error handling. So how is error handling done in C++ today? The standard method for error handling is with exceptions. Other methods include still error code, sentinel or return values, error output parameters mostly with pointers, and the global stable error null. Error propagation macros like ensure okay, expect equal. The stored pair that we used to return both an error code and the value, and other custom error handling types. Now, exceptions. Exceptions are often considered as harmful. So due to a few major reasons, which I really understand. So the first one is that exceptions have invisible control flow. It is seen both as, I see it as both an advantage and a big disadvantage, because ideally any expression can throw, and there's no way of knowing which expression throws and what exception it throws merely by looking at it. You'd have to inspect the expression source code to be sure if it is available. If you have to inspect the expression source code to be sure if the documentation for it is available, or if it is a proprietary library, you'd have to hope the library authors provide good documentation. Another one is that code using exceptions is usually non-deterministic. In hard real-time embedded systems code, you want to have a good idea of the amount of time each section of the code will execute for and its space or memory usage. You can't do that with exceptions, as most implementations use runtime type information with a heap-based allocation procedure. And as we all know, if allocation is non-deterministic in time, it can take a variable amount of time. It's not really specific. So another issue with it is type mismatch errors aren't like compile time checked. Exceptions are often used like there's little tiny difference between using exceptions and using dynamic typing, because you are basically doing type switching, and they are not really checked. So there's no telling when you use the wrong types for it. Another issue, a common issue people have with it is that it is often hard to manage in large and evolving code bases. So a lot of problems arise when a library implementer uses a certain exception for a failure that rarely happens, and then deprecates and switches to another exception type. So you as a user of the code will not know when this change occurs. due to the dynamic typing nature of exceptions. Another issue I have personally encountered is with the toolchain support. Some toolchains don't support exceptions, and instead resort to fail fast aborts when you throw an exception. An example is the extensor toolchain and the AVR toolchain. So yeah, another issue is that nothing prevents the users from handling fatal or not to be handled exceptions. Yeah. So what problems did exceptions really solve? I'll say they solve some problems for many people, which are exceptions reduce a lot of clutter and noise in the error handling code. So the exceptions also ensured errors can't be ignored, though it is not by compiler enforcement, but by tearing down the whole program if the exceptions aren't handled. Exceptions provide a somewhat unified error, and exceptions provide a somewhat unified error reporting interface. Yeah, I'd like to quote this message from Joe Duffy, which says, "Bugs aren't recoverable errors." I want you to remember that bugs are fatal failures and mustn't be recovered from. Using exceptions means a caller somewhere of the call stack knows how to handle the error. So you have to think more about using exceptions. So what really are exceptions ideal for? This is the question that we are left to. So the questions we have to ask is not really a straightforward question. We have to ask what we are using for. Are we using them for fail often or fail rarely? If so, how often are we talking about here? Are we using them for recoverable or irrecoverable errors? And also, are we using them in time constraint or non-time constraint scenarios? I personally don't have a concrete answer to this, but I feel we should try to answer these questions if we want to decide to use exceptions. Yeah, so result is STX solution to recoverable errors. Result is a type-safe monadic union for non-fatal failures. It either contains an error or a success value. So result is in many ways like option, but results represent the possible presence of an alternate or error value. The error value is used in constructing the error report as appropriate. It is in a sense very similar to boost expected, but with a centralized fatal error reporting mechanism, which we discussed earlier, the panic, and also has many monadic methods. So result is implemented as a safe union with a boolean to represent whether the union is storing a value or an error at a point in time. Result also has some constructors. As you can see here, the OK type is used for tag dispatch to the value variant state, which denotes success, and the error type, which is similarly used for tag dispatch to the error variant state in which there is an error. And as you can see, result only as a move constructor will go, it doesn't have a copy constructor, we'll go into that later. Yeah. So as I said earlier, you note that result doesn't have a copy constructor because it is primarily used as a return channel. Using for return channel as a return channel means the return channel must be as fast as possible without invisible copies of the object being passed, which would otherwise be costly for large objects, especially ones that perform dynamic memory allocation like stored vector. Let's look at some examples of how you'd use results in your code base today. We are writing a simple parser which just gets the first character and maps it to a version number. You can observe how we use the OK and error type for representing sources and error. Let's look at some of results. Let's now look at some of results methods. First off is the match method. which we used for handling both the case where there was a successful pass and where there was no successful pass. So yeah. Now let's look at another method, the unwrap method. It works similar to options unwrap as it calls the global panic handler if an error occurs. As you can see that the second operation will fail. So yeah. Let's see what the output will be. We get some useful information about the error, but what if we need to provide more information based on the function context at which the record unwrap? We can use the expect method. So here's how we use the expect method. It takes a string view as an argument which is used to provide context-specific error information. Yeah. Now we can see the output here. The only difference is that we added more context-specific information to the error message. Now let's look at error propagation with our error lane macro try OK. The pass file function illustrates how we do error propagation with the try OK macro. It basically returns the error type if the pass version function fails, and the result is constructed by tag dispatch from the error type. This is basically an emulation of the automatic error propagation we get from exceptions, but unlike exceptions, this is visible and concise. We know at what part of the program the propagation occurs. Similar to the option monad we demonstrated earlier, here is how you perform control flow with results. In the exceptions counterpart, the exception is automatically propagated. The results monad has similar abstraction capabilities via its monadic methods. So here's how you'd write the same code with output pointers on the right for error handling, which is in a sense quite verbose and very cluttered. Now let's take a brief look into how you do error reporting with the result type. You have a demonstration function named head, which we assume let's assume it performs a head request. It returns an error and we call the unwrap method on it. Let's say what is logged to the console, since there's definitely a failure there. Now this is the error we get. We get very little information about the nature of the error based on the value of the result. Now, as you can remember in the previous slide here, we returned a key access denied error, but on the terminal, we didn't really give much information about that. We can give more information or context about that with the report, with STX error reporting. So for your custom types, you can define a report method. You can define a report for it. So here's how you define the report operation. Here's how we construct an error report from the error type as illustrated. It's not necessary to write it this way. You can have a function that returns a string based on the error value and just construct the span report directly from there. Span report is a type erase view over a string or contiguous byte sequence. So now, as we've defined our report, let's see what we'll get on the console. Yeah, here's the error you get with the reporting. Do notice how we got information based on the error type. Now, you can check on more monadic methods at the documentation as usual. Yeah, so now let's perform some benchmarks and see how well results performs. So we'll be performing two nested foldable divisions and separating them into three different functions. The divergent is just basically x divided by y divided by z. So you don't really need to pay much attention to the code we'll be showing for this simple case benchmark. You can always view the code on the GitHub repository. The benchmarks were performed using the Google benchmark tool. So this benchmark will illustrate a few properties, which is the common propagation depth that we commonly see in code bases. It illustrates a common use case and the nature of the success and failure path for each method. So the failure path is basically when both divisions fail, and the success path is when both divisions succeed. So here's the benchmark code for state variant. You notice we use benchmark do not optimize because the compiler can try to optimize some variables away. So basically the action is never performed. Here's the benchmark code for exceptions. And here's the benchmark code for STX result. And here's the benchmark code for the C-style error handling, which is basically output pointers. Now, here are the results for the happy path, which is when both divisions succeed. You can see that they all perform within the same range for the success or happy path, as there is some minor system noise. But let's see how they perform on the sad path, which is when both divisions fail. As expected, the implementation using exceptions performed terribly for the failure or sad path. So let's quickly see what the actual values are on the table. We can see that the implementation using exceptions has a 554,384% latency increase compared to the C-style error handling method. But we should remember that their primary design consideration wasn't for fail often functions, but for fail rarely functions. So it's advisable to prevent using present exception implementations on auth code path. We can see that the implementation using results is just as fast as the implementation using the C-style error handling. I would like to leave us with a few notes from Jan Schwartzrock in the C++ exceptions and alternatives paper, which says there are more to exceptions than performance. The current discussion of exceptions tend to focus on performance. However, error handling is a prime software engineering topic. I recommend a greater focus on notation, on the role of constructors, destructors, and RI, on the effects on readability from literally the code with tests and annotations, on the guarantees offered, and on the complexity of the cost of passing information about an error of the code chain. So here are some useful links in case you want to know more about STX. Thanks for listening. I think we still have a few minutes to take some questions. So please drop your questions in the Q&A section in Remo, and I'll answer them if I can.